Good morning, students. Today our topic is qualitative analysis. And what is the qualitative analysis? So generally we have two types of analysis. One is the quantitative, another one quantitative analysis. So in first case, the quality, we can measure the quality of the product. For example, if you take any product, so we can measure the quality of the product. So the second case, so we are measuring the quantity, how much quantity we take. For example, if you take a sugar, how much taste it's a how much taste of the sugar. So generally, so in sugar, so which is where the uh, richest of the sugar. For example, we can measure it in the sugar. So sugar is the one of the example to understanding the easily quantitative and qualitative analysis. The quantitative analysis, so how much quantity we are taking the sugar. So what is the quality? What is the taste of the sugar? So that is the qualitative analysis. So generally, these cases we can understanding easily. And today we have to understanding the equivalence point and end point. So yesterday previous classes we completed. So this class we are understanding the what is the primary and secondary standards. So some of the compounds here primary and secondary standard compounds. If you keep in long time also, so the primary compounds does not change their concentration. That is secondary in secondary cases. So if you keep in long time the solution, the concentration may be change. So time to time. So that's why we are using as a secondary standard solution. So here the sum of the primary standard compounds, potassium dichromates, and these are the sodium oxalate and potassium penthalate, phthalate, and sodium carbonates. These are all the primary standards. And KMNO4 and sodium thiosulfate, and this is diammonium ferrous sulfate. So this is also one of the complex compound, and sodium hydroxide. These are all the secondary standard solutions. So today we also discussed about the acid-base titration. What is acid? What is base? So according to we have the three theories to classify the about the acid bases. Though according to Arrhenius theory, in solution it gives OH minus, it is a base, H plus proton it gives, it is a acid. So for example, if you take NaOH in a solution, it gives Na plus and OH minus. So it is act as a base. For example, HCl, H plus and Cl minus. It gives proton, it is act as a acid. So in acid-base titration, generally we are getting, so what is happening in acid-base reaction with two compounds to form salt plus water. Salt and plus water. So this is happening every reaction. For example, here we have understanding a simple reaction, and sodium hydroxide plus HCl, it gives NaCl plus H2O. So in this case, so the sodium hydroxide to reaction with HCl to form NaCl plus H2O. So in this reaction, NaCl is a salt plus H2O as a water. Every acid-base titration, generally we are getting salt plus water. So these are some of the example. How can you identify the neutralization point of these reactions? So here we can understanding easily. And so the acid-base titration, generally we are using a indicator. So what is the indicator? Generally, indicator is a weak acid or weak base. Weak acid and weak. So generally, the acid-base titrations we are using weak acids and weak bases as a indicators. According to Oswald theory, an acid-base indicator is a weak organic acid or weak bases. So how it's work? For example, if the pH change, so the color will be changed the indicator. So generally, indicator have the two colors. So if the indicator have molecular form one color and ionic form another color. So if you have the molecular form, so we have the show one color of the indicator. For example, if you take a phenolphthalein indicator, it is one of the best suitable indicator for the titration of acid bases. So phenolphthalein in molecule form, it is a colorless compound. In ionic form, it is a pink color. So if the solution, each ions, each molecules are more, so it represents their color. For example, if the phenolphthalein in the solution, if the solution, the phenolphthalein, the molecules are more in the solution. So for example, here we are getting the molecule color. If the solution in phenolphthalein in the ionic form is more, so they represent the ionic color. So that is the difference of the indicator. So that means if the molecules are more present in the solution, so that is a molecule color that is colorless phenolphthalein. Like for example, if ionic form is more in the solution, so it is a color compound. So that is a phenolphthalein. Just generally in ionic form, it is a pink color. So depending on this theory, so every indicator act as a good pH change. So their colors are changes. For example, here one of the example we are discussing about the phenolphthalein indicator. So the next one. So according to Oswald theory, so the internal structure, for example, here the weak acid, we take a simple example of weak acid, HIN. So dissociation into the in solution, it is a dissociation into ionic ion minus. So it release the proton. So the proton is bind to the H2O molecule. So it is H3O plus, represented as H3O plus. So the internal structure changes accompany dissociation and cause the color changes for base type indicators. For example, the base type indicators like this, it is an indicator IN, it is a base color. So H2O, so it is dissociation into INH plus and base color plus OH minus. So equilibrium constant generally Ka. So generally what is happening, the Ka is equal to product concentration by reactant concentration. Here H2O is a very large quantity, that's why we don't take the H2O concentration. So this is happening in IN like this, and H2O plus NH plus. So the dissociation constant Ka is equal to acid dissociation constant. If you take B is equal to base dissociation constants, like here Ka is equal in first equation, what is the representation, H3O plus and IN minus and HIN minus. By rearranging the equation leads to H3O plus concentration is equal to Ka. So here we are calculating the concentration of H3O plus. After that, the H3O plus is equal to Ka is equal to HIN minus by IN minus. So the indicator HIN show pure acid color when HIN by IN greater than 10, and the basic color when the HIN IN less than 0.1. So it indicates the pH acid color, the pKa plus 1, and pH basic color, pKa minus 1. So that means the color change at the range of the pKa depending on the pKa value. For example, if you take a acetic acid, what is the pKa value of acetic acid? 4.74. So the change will be, the pH range of the change will be acetic acid from 3.74 to 5.74. Because of we are lessing 1 from 4.74, adding plus 1 from 1 to the 4.74. So that is happening when it is so like here we take a simple example, phenolphthalein. Phenolphthalein is one of the example. So it is a molecule form, it is a colorless. It is a colorless compound in molecular form. Show here, colorless. So in a reaction with base, what is happening? So the lactone ring is opening. Lactone ring is opening. It is ionic form. Just we can see here the ionic form. It is happening. The ionic form is a minus colorless compound. After that, where addition of excess mole of OH minus, again the OH minus will open this this OH group and lose to finally it is a obtain pink color. So this is happening when the reaction will come under these reactions also. This is happening and how it is work in the phenolphthalein from the solution. So the next one. So for example, here it is a colorless in acid solution and is in the presence of dilute alkali, the lactone ring open to give triphenyl carbonyl solution. This is loss of water produce pink color in base solution. So that means the phenolphthalein, we are adding to the acid to the phenolphthalein. It is maybe it is a colorless compound because of it does not open the lactone ring to the proton. But in the addition of OH minus, what is happening? The OH minus, when you add the OH minus to the compound, this compound and phenolphthalein, what is happening? The lactone ring open. So that's why it obtained pink color. So this is happening in the phenolphthalein ring, and phenolphthalein it is obtained in color pink color. So this is about the phenolphthalein work, how it's work. So the next one here coming to, and this is the methyl orange. It is a weak base. So the methyl orange is a weak base and colored compound and act as a weak base. So like so many we have the weak acids and weak bases. All the weak acids and weak bases does not act as a indicator. So some of the compounds, they may be appearance color. So that compounds we are using as a indicators. So that is a fundamental thing about the indicators. So indicators, all the indicators are weak acids and weak bases. That is good. But some cases, it's what is happening in the colorless compounds, like we have the ammonia and acetic acid. These are also weak acids, but they doesn't, and it does not have any color. So that's why we are not using as indicators. But in the case of these compounds, like methyl orange, phenolphthalein, it is also weak acids, but it is appear as a color. So that's why we are using as an indicator. You choose that these compounds as an indicator. Because of this strong, because of this reason, so we are using these indicators. And methyl orange. So methyl orange in alkaline solution, the increasing in OH minus. So what is happening? It is here we show the equilibrium. So the methyl orange generally in two colors. In when it is molecule form yellow color, when it is ionic form red color. So ఒకవేళ the in ionic molecule, if the solution have the more molecules are present in the more molecules will present, so that is a yellow color is present in methyl orange. So generally if the ions are more present in that red color is appearance. What is happening? Let's we see what is happening. The methyl orange, how it's work in the presence of acids, in the presence of base. So what is the difference? So generally we know about the common ion effect. The common ion effect also very understanding to these theories. For example, in case of phenolphthalein or any phenolphthalein or methyl orange indicators weak acids. Generally, weak acids or weak bases are less soluble. That means less electrolysis. That means we cannot ionize dissociation and 100%. So it's maybe less percentage of association dissociation. Now let's we see what is happening in acidic solution in basic solution. This is the core structure of methyl orange ring. So here SO3 minus, SO3 minus group, and between the two um, benzene we have the nitrogen bridge. So this is the NH3 3O plus. So that is the quaternary ammonium salt. So what is happening? The quaternary ammonium salt when treat with the in a basic solution and acidic solution. This is the ionic form in red color. So in the molecule form it is a yellow color. So it is a easily understanding what is happening in the structure of methyl orange. So the quaternary ammonium proton loss here. So here the quaternary ammonium proton is lost from the quaternary. So generally quaternary ammonium salts act as a ammonium act as a base, but that's why this methyl orange also base. So in this it is act as a like acid and bases. So this is acidimetry and alkalimetry. It is estimated the alkali solution using standard acid solution and alkalimetry. So generally we have the acid base titration two types. One is the acidimetry and the second one alkalimetry. So in acidimetry we know the concentration of base, but we don't know the concentration of acid. In alkalimetry, in acidimetry it is the estimation of alkali solution. So the alkali solution we are using standard acid solution. We are using standard acid solution. In alkalimetry it is the estimation of acid by using standard alkali solution. The vice versa. For example, in acidimetry we know the concentration of acid, we don't know the concentration of alkali. In alkalimetry we know the concentration of the alkali, but we don't know the concentration of acid. So this way we can understanding to titration to conduct the acid base titration, which indicator is suitable for this compounds, because of the pH ranges are different for the different type of indicators from um, so for example we are conducting different type of titration from strong acid and weak acid, strong acid versus strong base, strong acid versus weak base. So we have so many types of titration. So that's why we need to change the titration methodology also. No, so these are the happening in the acid base titrations, and so in our syllabus we also some of the topics here, the chemistry thoughts and chemistry syllabus, and synthesis of organic compounds in new CBCS syllabus. It is a new CBCS syllabus. Last year it is on the fifth semester syllabus. Totally it is organic synthesis. Now it is changed to come to year third semester. So the synthesis of organic compounds and distillation. So these are all the some of the important things about the preparations. Distillation of salicylic acid and benzylation of aniline. These are all totally organic synthesis. Synthesis of organic compounds, acetylation of salicylic acid and benzylation of aniline. In acetylation of salicylic acid, we are preparing aspirin compounds. Benzylation of aniline, we are getting so many benzylidine products, and this is the aromatic electrophilic substitution reaction. So these are very broad classification reactions, aromatic electrophilic substitution reaction. So in this case, nitration of benzene. From benzene, we are conducting nitration to prepare the nitrobenzene. After that, that preparation of nitrobenzene, and we are conducting again nitration on the nitrobenzene. Finally, we are getting meta-dinitrobenzene. So this is the third one, halogenation. This is also very important one. And preparation of para-bromo-acetanilide. Para-bromo-acetanilide, preparation of 2, 4, 6 type bromophenol. So from acetanilide, we are preparing para-bromo-acetanilide. And this is the phenol and the bromination. Finally, we are getting the 2, 4, 6 type bromophenol. It is very well-known famous named reaction also. This one, oxidation. Preparation of benzoic acid from benzyl chloride. Also, preparation of benzoic acid from benzyl chloride. So, benzoic acid from benzyl chloride, this is the oxidation process. So, what is happening? The chlorine will change to oxidation OH minus and oxidation, preparation of benzoic. So this is esterification, preparation of N-butyl acetate from acetic acid, and methylation from methyl of naphthalene, naphthyl methyl ether, condensation, preparation of benzylidene aniline and benzylidene and aniline, diazotization,